Hello, chemists. This is Ms. Placino, and you're watching lesson 8.3 on types of nuclear reactions. In today's lesson, we're going to go beyond natural transmutations that we covered in 8.2, and we're going to look at other types of reactions that can occur in the nucleus. Goals for today's lesson include identifying nuclear equations as artificial transmutations, fissions, or fusions. We'll be able to predict the identity of a missing particle in an artificial decay equation. And kind of a more advanced thing to do, we're going to be able to translate nuclear reactions into equations. So basically, I'll give you like a sentence, and you're going to turn it into a nuclear equation. Probably the big one for today is identifying missing particles. All right, let's get started. Of course, since we're talking about nuclear chemistry, we've been studying the nucleus. If you think about the structure of the nucleus, you have all of your protons in one location. Of course, protons are positively charged, and you know from experience that like charges repel one another. So in order to overcome that repulsion, we've got something called the strong nuclear force, and it's going to hold the nucleons together. And when we say nucleons, we're just referring to the protons and the neutrons. So we've got our nucleus where they're all kind of in very close proximity to one another, the protons and neutrons. And we can also have them as separated nucleons, as individual protons and neutrons. It takes energy to break apart the nucleus. It's called the binding energy. Basically, if we put the binding energy in, like that amount of energy into the nucleus, we're able to take the nucleus and split it back apart into subatomic particles. Nuclei that are more stable require more energy to break apart. Hopefully that makes sense. If you've got something that is very, very stable, you're going to have to pump in a lot of energy to split it into its nucleons. If you have a rather unstable nucleus, it requires less energy to break apart. Just a little bit of background on the nucleus. Anytime you form a nucleus, it's going to release energy. So if you just take subatomic particles, protons and neutrons, and you join them together to make a nucleus, energy gets released. So here we have an isotope of hydrogen, H2, sometimes called deuterium. H2 is composed of a proton, a neutron, and an electron. So I'm not too worried about the numbers themselves. We can take the mass of the individual subatomic particles, total them up to get about 2.016 atomic mass units. However, if I look at the mass of an H2 atom, so like the actual nucleus and the electron to make up the atom itself, we'll see that there is a difference in mass. Somehow adding the proton, neutron, and electron together to get a deuterium atom results in the loss of mass. We call this mass defect. So again, the mass of the protons plus the neutrons, I guess you can throw the electron in there too as well, though it's very, very light, is going to be greater than the mass of the nucleus. What we end up seeing occurring with that mass that is missing, and I'm using that kind of in quotes, is that it gets converted into energy. I'm guessing many of you are familiar with that equation. You've seen it before, E equals mc squared. This is actually talking about what's happening to this small missing mass as we take our subatomic particles and we form a nucleus out of them. E stands for energy. Oops. M is mass, and c is the speed of light. Now, it's been a while since we've talked about the speed of light, so just to remind you, it's 3 times 10 to the 8th meters per second. So through these very, very small mass defects, we're actually able to produce a pretty substantial amount of energy. I'm not going to ask you to perform calculations with E equals mc squared. I just kind of want you to get an appreciation for what's happening when a nucleus forms. We are going to see a little bit of mass getting effectively lost, but in reality, that mass is converted into energy. Right. So let's talk a little bit about artificial transmutations. We know that a transmutation is changing the identity of an atom or the identity of a nucleus. The only way to achieve that is to change the number of protons that are present in that nucleus. So in lesson 8.2, we looked at natural transmutations, sometimes called spontaneous transmutations. Those happen without us doing anything to that radioisotope. So if we're going to look at artificial transmutations, what do you think that might mean? Yeah, this is changing the identity of a nucleus or an atom artificially. So we're doing something to induce or to cause that change in identity to occur. So usually artificial transmutation will take place when we take a nucleus and then we bombard it or smash something into it. And that needs to be high energy particles. So we can take a nucleus, we can smash a particle into it. It takes a very high speed, and we can force nuclear decay to occur. One kind of hallmark of a artificial transmutation is that we will always see at least 2, if not more, reactants. So when it comes to trying to classify artificial transmutations, that's something you can be on the lookout for. This equation here is an artificial transmutation. I have multiple reactants. In most of our spontaneous transmutation or natural decays, whatever you'd like to call them, we tended to see just one reactant breaking apart into 2 products, with the exception of electron capture. We're going to try to solve for this question mark, the missing particle. We're going to go about it really the same way that we did for lesson 8.2. We want to make sure we're balanced for mass, so the top numbers, and balanced for charge, the bottom numbers, on both the reactants and product side of the equation. Hopefully this math isn't too bad. 4 plus 27 gives you 31. I already have a mass of 30 on the product side, so my unknown particle must have a mass of 1. 2 plus 13 is 15, which happens to be the same number of protons that I have on the product side already. So I must have no charge or no protons in my missing particle. What do we know of that has no charge and a mass of 1? It's a neutron. If you were struggling a little bit with that, don't forget, you can go back to reference table O and you can see different symbols, including the neutron, that will come up in some of our nuclear equations. Let's try out some practice problems with this. Okay, so here we are in the practice problems, and I want to take a look at question number 1, really focusing on trying to solve for the missing particle. We're going to go over questions A, B, and C. I want to start with question B first. So I've got a magnesium nucleus reacting with a lithium nucleus to produce a silicon nucleus and some unknown particle. We're going to go through the same procedure. Make sure the masses are the same on both sides. Make sure the charges are the same on both sides. So 24 plus 7 is 31. I already have a mass 30 on the product side, so X must have a mass of 1. I've got 15 for a total number of protons on the reactant side. I've got 14 over on the products. So my particle must have a charge of 1 as well. If you take a look at table O, you'll see that this can either be a proton or hydrogen. Doesn't really matter. So that is perfectly valid, as is that. If you're going to use the symbol P for proton, make sure it is lowercase, and this isn't like a capital P and you're kind of mistakenly expressing it as some very strange isotope of, actually an impossible isotope of phosphorus. Try out question 1C. All right, so hopefully you notice that there is a coefficient of 2 in front of our unknown particle. So this makes it a little bit more difficult. I've got a mass of 6 on the reactant side. I have a mass of 4 on the products. So total, I have to have a mass of 2. 1 plus 1 is 2. I already have 2 on the product side. So 0. I'm going to take my mass number and my number of protons divided by 2 to get the values that I need for the particle. And we talked about this one just a couple minutes ago. No charge, mass of 1, that's a neutron. Pause the video, try question A, being very careful that you have a coefficient hidden away in there. All right, so your mass of this missing particle should be 102 AMUs. Should have calculated 37 protons in its nucleus. I can use the reference table, look up which element has 37 protons, and hopefully find that it is rubidium. Okay, hopefully this feels really, really similar to what we were doing with lesson 8.2, ever so slightly more involved as we see multiple reactants, and we've got some coefficients from time to time to work with as well. All right, let's get back into classification. All right, so all of the reactions that we are going to look at in the practice problems are going to be some sort of artificial transmutation. But we can be more specific about it. We can also classify artificial transmutations as either being fission or fusion reactions. Let's start with fission. In a fission reaction, you have a large nucleus, sometimes referred to as the parent nucleus, and it's going to split apart into two smaller nuclei that are sometimes referred to as daughter nuclei. So if we try to represent this like with a picture, here we have our parent nucleus, this uranium-235, and we're going to hit it or bombard it with a neutron. When that occurs, since the neutron has no charge, if it's moving fast enough, it might be able to get through the sea of electrons around the nucleus and kind of attach itself or bind onto the uranium-235 nucleus. This has a destabilizing effect, and that's what we're trying to depict here with this very strangely shaped, almost looks like a dumbbell nucleus. Now it's uranium-236 because that extra neutron has been added, and this plus sign is just supposed to mean high energy. We did not create a positively, an ion of a nucleus. Nuclei are always positively charged. So this destabilization can lead to our fission products, also known as our daughter nuclei. And in the case of uranium-235, we produce 3 additional neutrons. What do you think those neutrons might be able to do? Yeah, there's a chance that they can go and find a uranium-235 nucleus to react with and kind of repeat this process. That's really the driving force behind something like nuclear power. We can have this reaction occurring in a very controlled manner, or nuclear weaponry, or we kind of just let this reaction run wild. When it comes to identifying a fission reaction, the key is to look for your very large parent nucleus. Generally speaking, fission reactions are kind of just reserved for 2 elements, uranium and plutonium. Both of these are very, very large nuclei, and they're going to be able to split into smaller ones, and certain isotopes will produce these additional neutrons as shown in this picture. This is the key to fission. Look for uranium or plutonium plus a neutron as your reactants. Kind of the opposite of fission is the concept of fusion. When fusion occurs, we've taken 2 small nuclei and we've joined them together. Of course, joining 2 smaller nuclei together is going to result in a larger one being produced. Fusion occurs very readily in the sun. We see isotopes of hydrogen. So we have deuterium, which is a proton and a neutron. It have a mass of 2. We also have another isotope of hydrogen called tritium with a proton and 2 neutrons for a mass of 3. We can get those 2 nuclei to collide, hopefully overcoming the repulsive force because of the like charges. Get them close enough together where the strong nuclear force will take over and it will produce a new nucleus. In the example here, we produced helium. We still have that other neutron kind of left over, so that can just be ejected as well. And very similar to fission, we're going to release huge amounts of energy through the process of fusion. Fusion is difficult because we need high temperatures, and it's difficult to control. I mean, this happens readily on the sun, and as you might imagine, getting to temperatures that high and still being able to kind of control the material is going to be extremely difficult to do on Earth. Fusion is really only practical with our smallest possible nuclei. So that's going to limit us to hydrogen and helium, hydrogen being far more common with fusion than helium. So if you're looking at an artificial transmutation, you've identified it as such because you've got multiple reactants, and both reactants happen to be both reactants happen to be hydrogen. My mistake. There's an extremely high likelihood that you're looking at a fusion reaction. Okay, so fission and fusion are kind of the opposite processes of one another. Fission splits apart, fusion joins together. But one thing they both have in common is that they produce tons and tons of energy. You might be thinking, well, wait a second, how is that possible? They're the opposite processes, so shouldn't one produce and one require? You would think that way from maybe some chemical reactions that you're familiar with, but that is not the case when we're talking about changes in the nucleus. Both fission and fusion result in the formation of more stable nuclides. So basically, you can think about the top of this chart being very stable. And as you get closer to the bottom, closer to the x-axis, you see unstable. So in the case of fusion, we're taking our really low mass nuclei, we're fusing them together, and we're starting to move in this direction. So we're moving towards a more stable nucleus, so energy will be released. And in the case of our fission reactants, heavy isotopes of uranium, when they split apart, we're moving in that same direction towards a more stable nucleus, so energy can be released. For whatever reason, this concept can sometimes be really difficult for new chemists to wrap their head around. So again, our products of both fission and fusion are going to have a greater binding energy, which just simply means they're more stable. Since they're more stable than the nuclei they were produced from, energy must have been released. So again, if you're kind of having trouble visualizing and thinking about what to do with this graph, don't stress. Just understand that both fission and fusion release energy as they create more stable nuclei. All right, let's wrap up with the practice problems. Okay, so we're back in the practice problems. We already went through and did kind of the heavy lifting for question 1. We figured out what the symbol is for the missing particle. Let's go back and try to classify it. So if we take a look at question A, I see uranium, a very large nucleus, as a reactant, and a neutron. Yeah, this is going to be a fission reaction. We've produced daughter nuclei in cesium and rubidium, and we've created more neutrons. This is like a textbook example of fission. If we look at letter B, magnesium and lithium, well, those are definitely too big to be hydrogens and too small to be uranium. It's not a natural transmutation because I have multiple reactants. So kind of the catch-all will be an artificial transmutation reaction. That's the best we can do for classifying this one. And question 1C, I see 2 different isotopes of hydrogen fusing together to make a larger nuclei, and we also produce a couple of neutrons. Yeah, that is a fusion reaction. Excellent. Okay, definitely take some time to practice with those 4 remaining equations. Okay, let's wrap up with doing a translation. So in my opinion, this is about as hard as I can make it. I'm going to give you a sentence in just plain old English, and I'm going to ask you to write a balanced nuclear equation and classify the type of reaction that is occurring. Let's take a look at question 2b. All right, so we're told the bombardment of chlorine-35 with a neutron produces a sulfur-34 nucleus in another particle. Okay, so we're bombarding chlorine-35 with a neutron. All right, so I've got 35 as the mass of my chlorine and a neutron. So mass of 1, charge of 0. If I use the periodic table, I can look up the atomic number of chlorine and find that it's 17. Produces, that's kind of your sign of like, oh, it's a reaction arrow. A sulfur-34 nucleus and another particle. So sulfur-34. Again, I can go back to the periodic table. Sulfur right next to chlorine. Element 16. Make that a little bit neater. And another particle. So now we're going to try to solve basically for X, really similar to what we were doing with the above problems. Get a mass of 36 on the reactant side, mass of 34 on the products. So I must have a mass of 2 for my particle. Total charge of 16 on the product side, so I must have a charge of 1 proton in its nucleus. Oh, this is one of those isotopes of hydrogen, technically deuterium. All right, so I produced hydrogen. So I've got my reaction translated out of English and into nuclear chemistry. What's the best classification for this? Here are some traps that I often see students fall into. Oh, there's a neutron on the reactant side. It must be fission. No, double check. We haven't split into daughter nuclei. Chlorine is way too small to be involved in fission. It has to be uranium or plutonium, so it's not fission. Another common mistake I see, isotope of hydrogen. This must be fusion. No, fusion occurs when hydrogen are the reactants, where we're taking multiple hydrogen nuclei and we're fusing them together to create a larger nucleus. That is not what's happening here. Hopefully it's obvious that this is not some form of natural transmutation. So again, by process of elimination, we're just left with the artificial transmutation. And feel free to abbreviate so that it'll actually fit in the box. All right, chemists, I'm sorry this one ran a little bit on the long side. Keep practicing with this material. Thank you for tuning in, and I hope you found this helpful.